method for this Kaplan-Meier, that is the product limiter for this Nelson-Allen. And now let's continue to this Nelson-Allen, similar to Kaplan-Meier. Okay, here we go.
2.3 Nelson-Allen. An alternative to the Kaplan-Meier estimate is a modification of the Nelson-Allen estimate. This method directly estimates the cumulative hazard rate function of an incomplete data. So for this Nelson-Allen, we try to estimate the cumulative hazard rate function. So we let Rx be the risk set, and let Xi be the uncensored value, such that Xi is unique and ascending. And if we let this Nxi be the number of Xi, then the cumulative hazard rate function is defined as the summation of the Nxi divided by the R. So if you look at these piecewise functions of the cumulative hazard rate function, that is in terms of summation. So which is different from the Kaplan-Meier. And also the Nelson-Allen has the recursive formula, that is this. Let's go to example 5. Determine the Nelson-Allen estimate of the survival function for the data in example 1. So from example 1, we have this data. So that is this data we have found in example 1. Next. So therefore, we have to estimate this cumulative hazard rate function in terms of piecewise function. For the first interval, that is from 0 to 0.5. So the first value is always 0. Now for the second interval, that is in between 0.5 to 2, we will have nx1 divided by r1. So from the table we have our nx1 is 1 divided by r1, which is 1 over 4, and which is equals to 0.25. So for the next range, that is from 2 to 3.2. Now for the next interval, we use the recursive formula to calculate. That is, we take the previous result plus the new result here. So we have 0.25 and then plus the nx2 divided by r2. So you can see the nx2, which is equals to 2, and then the r2 will be 5. So it will be plus 2 over 5. So you will have 0.65. Let's go to the last interval, that is from 3.2 to infinity. So again, we use a recursive formula that we take this result 0.65 and plus the nx3 divided by r3. So here we have 0.65 plus the nx3 we found, that is 1, and the r3 is 5. I mean this is 1 over 5. So we will have 0.85. So that means this is our accumulate hazard rate function. So our aim actually is to find the survival. And we know that the cumulative hazard rate function is equals to negative log survival. So therefore, the survival actually is equals to e to the power of negative hazard rate function. So therefore, we can get the survival function by taking this e to the power of 0 for the first interval. That is 1. So for the second interval, that is from 0.5 to 2. That will be exponential to the power of negative 0.25. And the third interval, that is from 2 to 3.2, we will have exponential to the negative of 0.65. And similarly, for the last interval, that is from 3.2 to infinity, we will have this exponential to the power of negative 0.85. So this is the result.
Okay, that's as long as you know how to calculate the reset value, then apply to the formula for this Nelson-Allen. Now you have to be careful. That is for Nelson-Allen, the piecewise function actually is to calculate for the cumulative hazard rate function. But if you compare to the Kaplan-Meier, the Kaplan-Meier we calculate the survival. Okay, so please highlight. Okay, for Kaplan-Meier, the reset value is applied to the survival, but for this Nelson-Allen, the reset value actually is applied to this cumulative hazard rate. But from this piecewise function in terms of this cumulative hazard rate function, that we can use recursive to calculate. And after that, next we can use the question may ask you to find the probability of survival. So then after that, we can use a formula convert to this survival. That is in this example that we show already, that this formula. Okay, so you have to convert, okay, from this cumulative hazard rate to become this survival. Okay, using this and apply the result for each interval. Okay, apply here, then you will get the survival. Okay, as this in term of this piecewise function. So if you this example we pick from the example from Kaplan-Meier. So if you look at the result last week I have shown you. Okay, so this result actually is totally different from the result. Same interval with the same interval survival, but the different result compared to the Nelson Kaplan-Meier. As I told you, different method, slightly different the answer, because I told you this is not 100% accurate. Okay, just approximately only. Okay, so we will say which method is the best. Okay, both also approximately. Okay. So so remember for Kaplan-Meier, the reset value we try to calculate for the survival. Okay, but for this Nelson-Allen we calculate the cumulative hazard rate. Okay, this is the first slide I want to let you know. So let's go to another slide. So we continue to next example, 6.
Consider the observation 2005 until 7005. There's no truncation is possible. Determine the Nelson-Allen estimate of the cumulative hazard rate function at 7000, assuming all the observations are uncensored. So the solution for part A, First of all, we try to let x be the random variable representing the Chapt observation from here. You can see that, for example, the observation for 2005 repeated 3 times. So we try to make this as an x value, which is a distinct. So that is become 2005 and until 7005. That means under this x value, we have 8 data. Now, however, 2005 repeated 3 times, 5000 repeat twice, and 7000 repeat twice. The rest are 1. So this question is said that assuming all the observations are uncensored, that means there's no truncated value and no censored value. So we know that our reset value, which is equals to conditional nxi plus the conditional nui and then minus the conditional ndi. Since these two are 0, so that means the ri straight away is equals to nxi. And now we try to count what is the conditional nxi. So first, we choose our x1 as 2005. Under this condition, how many x value which is more or equals to 2005? Of course, all. That is 12. Say I choose this x4, 4517. So how many x value that more or equals to 4517? That is here. So we have 7. So and so on, you can calculate the rest. So the reset value actually straight away is equals to 12, 9, and so on. Part A. We have to find what is the cumulative hazard rate at 7000. So we know that this 7000 actually is force on this group. That is the second last group from 6932 to 7500, and this is a lower bound. So you have to consider all the reset value from 12 to 3. Here we have 7000, which is force on this group, 6932 to 7500. So we sum up all the xi value divided by the ri. So then we have 3 over 12 plus 1 over 9 plus 1 over 8 plus until the second last, which is a 1 over 3. So you add up this, you will have 779 divided by 504. So now we go to part B. We want to determine the same estimate, assuming the observation at 2005, 5000, 7005 will be the right censored. That means these 3 values now become the right censored. That is a U value. So you have to construct another table. So for part B, now you can see that this is our original 12 data here. The question says that if 2005, 5000 and 7005 are the censored value, so the remaining is become the uncensored value for the Y. So from here, you can construct another table. So this new table that I convert to the X. Again, we have to calculate all the conditional frequency for the X and U. So for this question, we have the censored value, but we do not have the truncated value. If I choose this is my X1, then how many X value which is more than 3617? So from the X value, I have 5, which is more or equal to 3617. So if I choose X3, equals to 4517, then how many x value which is more or equals to 4517? So I have 3. I have 3 data which is more or equals to 4517, and so on. Next, we calculate the conditional NUI. Say I choose my x2. So how many use value that more or equals to 3662? So from the question just now, we have 1, 2, 3, 4, which is more than 3662. Therefore, we have 4. Let's choose this x4 as 6010. Then how many use value which is greater or equals to 6010? So we refer to this again. We have only 2 values which is greater than 6010. Therefore, we have 2. And so for the rest. So how to find this reset value? That is by this formula, because we do not have any truncation value. So therefore, this conditional NDI is become 0. So this become the reset value. So in other words, we just sum up these 2 columns. That's become the reset value. Like 5 plus 4 is 9. 2 plus 2 is 4, and so on. For B, we need to calculate this hazard rate as 7,000 as well. And now you can see that this 7,000, which is falls on the last group, that is 6932 to infinity. So this is a lower bound. That means you have to consider all the reset value. So by taking what's the sum of the NXI divided by the reset value, then you will get the answer. So here we have 6932 to infinity. That means now we add up all the XI divided by the reset value. So you will have 1/9 plus 1/8, 1/7, 1/4, and 1/3. So this become 485 divided by 504.
Okay, so part B is a bit complex compared to A. Part A I think should have no problem. Okay, so part B is saying that we have some value is become the censored value. Okay, so for part B, that these 3 value then become the right censored value. Okay, so that means for part B here we have to consider the U and the D is still 0. Okay, so then after that you need to construct this table. Of course, this table is not necessary to construct, but here I just explained to you. Okay, from the original data, this 250, 5,000 and 7,005 now is you have to take out from the uncensored value become the censored. Okay, so that means now you have you have this data, and of course this one you can convert to another table, that is your X become distinct. Okay, so I think if you really pay attention, okay, I think you have no problem, class. Okay, once you can construct the table, and if you can calculate all this conditional frequency, then you should know how to get the R. Okay, and also yesterday also we have a similar question that you must know how to look at the question, class. Okay, so this question actually you have to know that like 7,000 in this range, that means you have to consider the lower bound. of this string 6932. Okay, so you have to look at the 6932 for part A. Okay, that means 6932, the 7000 is forced on this group, right? From 6932 to 7000. So you have to consider the lower bound. That means you have to consider all the reset value from 12 until this lower bound, that is 3. Okay, and then for the part B, that you can see the okay, this 7000 is forced on this group. Okay, a 6932 to infinity. Okay, so you have to okay, that is this group. Can you see? Okay, so 7000 falls on this group, last group, then you have to consider the lower bound of this. That means you have to consider all the reset. Okay, so then you can calculate by taking this is, you can see this is a sum. Okay, this is a sum. The Nelson-Allen is to sum up. For the Kaplan-Meier, you need to multiply. Okay, you have to look the piecewise function that carefully. Okay, do not simply this is sum. You plus. Okay. So this is example example 6, I think. Okay. So now we move to another slide. Any questions? Okay. Okay, since no question, then we move to next slide. So we have two more examples, 7 and 8. Now, some question you no need to count the reset, so it's already given. Okay, so for this type of question, you save a lot of time because you no need to calculate the reset. You need to calculate the conditional frequency. Okay, we just apply the result whatever given. Okay, you look at this question, please.
Example 7. For a mortality study with right sensor data, you are given the following. This is a X data for a time random variable, and this is a number of observation of this Xi. And here is the reset value which is given, and we have no need to calculate for it. This question is asked to calculate the value of K if under this Nelson-Allen estimate of the survival function at time 10 is 0.575. So here we go. So for number 8 here, be that X be the random variable of a mortality data, so such that the estimate of the survival at 10 is 0.575. So our aim is to find what is this K value. So very obvious that this 10 actually if it falls on the last group, that is from 10 to infinity. So that means you have to consider this lower bound at this last group, that you have to consider all the reset value. So that means you have to take 1 over 50 plus 3 over 49 and so on until plus 7 over 21. So here you have the 10 inside the group, which is 10 to infinity. So therefore now calculate this cumulative hazard rate function at 10, which is equals to 1 over 50 plus 3 over 49, 5 over K plus 7 over 21. So if we simplify this, we will have 3047 divided by 7350 n plus 5 over k. And we know that this is equals to negative log survival at 10, and this is equal to this 3047 divided by 7350 plus 5 over k. Therefore, we calculate this, you will get this k is equals to 36.0159. So remember, all the value here must be integer. So k also integer. So therefore, k is about 36.
Okay, so I hope you get it. Now, so this question, if you okay, go back to the questions. So the question is only given this, okay, only given this. So you don't ask whether the question is need to involve the truncation or censored, okay. We don't bother about this because whether you have or don't have, we don't care because the reset value is already given, okay. So this question, they already skip the information about the truncation and the censored value, okay, because they already give the ask reset value. Okay, so whether involve truncation, censored, or didn't involve, that is not an issue anymore because the reset is already given. So in other words, we straight away apply, okay, the reset value to this Nelson-Allen. Now, from here, quite obvious, right? So this info is already given, that survival at 10 is this, right? So what you want to do is you have to calculate the cumulative hazard rate by this, okay, formula, okay, and you just solve the equation, substitute this value inside here. After you change to the survival, okay, you substitute, then you can solve the k. Okay, the k must be integer. You have to know that. Okay, therefore, your k is about 36. Okay. Now, next, we'll go to another example. Okay, let's look at it.
So remember, all the value here must be integer. So k also integer. So therefore, k is about 36. Example 8. You are given a mortality study covers n lives. Second, none were censored and no two deaths occur at the same time. Third, let xk be the time of the k death. Plus, a Nelson-Allen estimate of the cumulative hazard rate function, which is given by this at x2 is 39 divided by 380. We need to determine the Kaplan-Meier product limit estimate of the survival function at time x9. So altogether we have n lives, and none were censored. There's no censored value at all. So all the uj will be 0. And of course here, the question didn't mention about the truncation value, so that dj also equal to 0. That you can see here, no two deaths occur at the same time. That means all the death value, that is uncensored value, which is distinct. There's no repeated value for the x. And xk is the time of the k death. This is repeated, it's 2 points. That x1 is referred to the first death. There's a first x1 value. The second means the x2 is the time of the second death. So this is a solution for the example 8. So let x be the random variable of a mortality data such that this cumulative hazard rate at x2, which is equals to 39/380. So we know that there's no truncation and there's no censored value. So therefore, the reset value will be equals to the conditional nxi. So if you plot the table, and this is my xi, this is the frequency of the xi, and the last will be the conditional xi. So when I is 1, I have x1, and this will be 1. When for x2, I have 1 as well. x3, I have 1, because there's no two deaths occur at the same time. So until xn minus 1 and xn here, all the data 1. So the I is from 1 to n. How to calculate this conditional for the nxi? So when you choose the first x1, how many data are more or equals to x1? That means all, that is n. So if I choose x2, how many x value that is more or equals to this x2? So I have this, that is n minus 1. So if you choose x3, then how many x value which is more or equal to x3? That is here. So it's become n minus 2. And until the last one will be 2 and 1. So we know that without the truncation and the censored value, so the reset value is equals to this conditional nxi. So therefore, this also equals to the reset value. So if given that this cumulative hazard rate function at this x2 is 39/380, so therefore, under this Nelson-Allen, that will be 1/n plus 1/n minus 1, which is equals to 39/380. So if you read
the class, in this one you need to consider there's only two. Okay, only first two line you have to consider, not all, because we are trying to calculate the cumulative hazard at x2. Okay, therefore we only consider n and n minus 1 from the reset. Okay, not all, please continue.
380. So if you rearrange this, you will have, this is a quadratic equation, that is 39n squared minus 799n and plus 380, which is equal to 0. So we can factorize this, which is equals to n minus 20 and 39n minus 19. So therefore we have n is 39/19 or 20. Now since n is 39/19, which is not integer positive, therefore we will choose n is 20. So if you look at this question, is our aim is to use Kaplan layer instead of Nelson-Allen to calculate what is the survival function at x9.
Okay, so here I want to highlight in tutorial question there are many some questions are mixed together. Okay, the info is given in terms of Nelson-Allen, but they asked to calculate by Kaplan-Meier, or maybe another way around. You have to see the question carefully. Do not simply assume. Okay, so once you have found the n already, just now is 20, and now all the information they have, and now I apply the Kaplan-Meier to calculate the survival at x9. Carry on.
So that means we use Nelson-Allen to find the information, and next we use Kaplan-Meier to solve this problem. For Kaplan-Meier, that is, we need to calculate what is this survival at x9. This is our aim. So if you come back to here, you can see if you substitute your n is 20, and this of course is 19, and this is 18, and so on. But where is our x9? So our x9, say somewhere around here. So you could see that this total is always 21. 20 plus 1 is 21, 19 plus 2, 21, 18 plus 3 is 21. So this 9 will give you 12. So that means...
Okay, so this is a trick class. How you want to calculate. Okay, so in tutorial question also we have something like that. So you have to trace. You can see, right? 20 plus 1 is all 21, and 19 plus 2, 18 plus 3. So this must be 12 because 12 plus 9 must be 21. So that means this set at x9 is 12. So we only need to calculate from 20, 19, 18 until 12. The rest we don't consider. Okay?
At x9 here, our reset value actually is 12. So we have to consider this reset value from 20 up to 12 to solve this problem. So that means this will be, under this Kaplan-Meier, that will be 1 minus 1 over 20 times 1 minus 1 over 19, and until the last will be 1 minus 1 over 12. So you can simplify here, this become 19 over 20 times 18 over 19 and times this 11 over 12. So you can see that this numerator will cancel with this denominator, and all this will be cancelled. Left only 11 and 20.
Okay, so it's so simple. As long as you have the n value, then you can calculate for the survival at x9 under Kaplan-Meier. Kaplan-Meier is, you can see, is product. Okay, product. But for Kaplan-Meier is sum. Okay, so please take note. Okay, so any questions for this? So if no, then I move to next. Okay, so before we go to next is another section now, class. Is talk about you have some observation entered at the beginning. Okay, so maybe after I take the attendance, then we continue from these two. Okay, so you give me about 5 minutes. Okay, let me take the attendance.